Basically, we discussed some key exchange protocols. So basically, to exchange symmetric keys or symmetric cryptography keys, and we saw that in most of the protocols we saw, there is a need for a trusted center. So in order to for two entities to exchange a key, they need a trusted center. They need an entity in the network somehow that will be trusted, and it will like basically share the keys. Now the second part was about what if we don't have that trusted center, and a scenario where two entities needs to exchange any secret keys here, and there is no trusted center. They need to exchange by themselves. So we saw this algorithm or this protocol, the Diffie-Hellman, very common, very practical protocol. It allows two entities, Alice and Bob, to agree on a secret key without having agree on a secret key, and all the traffic is not encrypted, is in plain. Okay. So anybody watching the traffic in the middle here, although he can see everything, all the bits, without encryption, he will not be able to guess what is the secret, basically, the secret key. Now remember how it works, Alice. So there are two values which are public, P and G. Okay. Then so basically these two values can be generated by Alice, and then it just send it to Bob. Okay. Then Alice will generate, will pick a secret random number, which is X. It computes G to the power X modulo P. It gets a value R1. It will send it to Bob. Okay. So X is secret. X will not be sent to anywhere. Okay. Only R1. Okay. Which is a value computed out of X. Okay. Now Bob will do the same thing. Will pick one number Y. Will compute R2. Will send it back to Alice. And then both of them will do the same thing, which is taking the value they got from the other party, and do the computation. So basically, power X, which is the random number picked by that user. Okay, it will generate the value K, which is the secret key. Okay, so basically, if Bob does the same thing with the R1 it received, it will end up having the same value, and basically anybody in the middle here, any attacker, will not get that secret value, because it's computationally infeasible to guess K if you just have R1 and R2. Okay, you need X and you need Y.
Okay. There is an attack for this one. I mean, you can, if it was in the middle.
Yeah, there is an attack. Yes, of course. So basically, this is a secret key. This is just an example. This is example of showing how large are the values that are picked. Okay. So see R1, R2, they are really large. Okay, and this is the key. Basically. Okay. Now this is the the idea here is that the secrecy of the key is composed of from three parts. Okay, from three parts. If you have those three parts, you have the key. Okay, so those three parts are G, which is public. So 1/3 of the secret key is public. Okay, 1/3. So you need to guess the two others, the two other parts. The two other parts are X and Y. Okay, so basically, Alice will know G, will have X because it's it picked that number, that random number, and then the third part Y, it can get it from R2, which has been sent by Bob. Okay, so and then it will complete the three parts of the secret key, and it can compute the secret key. The same thing for Bob. So for an attacker, in order to know the secret key, it needs the three components, or the three secret parts of the key. Okay. Now, an attack, very simple attack, which is, by the way, an attack that can be working for any protocol where you don't have authentication, basically. Okay. So here, authentication is not satisfied here. Okay, so this is why an attacker can carry out a man in the middle. Man in the middle, say MITM, we're going to see it in the future. It stands for man in the middle, so basically the attacker will place himself between the sender and the receiver. Okay, so in the man in the middle here, the attacker can basically not break Diffie-Hellman, it will take advantage of the absence of authentication to claim to be Bob for Alice and to be Alice for Bob. Okay, so it places himself in the middle here, and then when Alice needs to send R1, Eve will get that value R1, and it will finish the communication with Alice, and meaning here it will have the secret key, a secret key between Alice and Eve. Okay, and basically Alice will think this is the secret key with Bob. Okay, now the same thing. It will establish another Diffie-Hellman secret key sharing with Bob. It will do the same process, and it will get another key for the communication between Eve and Bob. And basically, it will, for all the traffic, it will, if for example it wants just to see what's going on between Alice and Bob, it will just watch out the traffic, which is basically which kind of attack? It's passive attack. Basically watching out what's happening, not modifying anything. Okay, passive. It can do that, and also it can, since it has access, once the traffic reaches here, it can decrypt that. It can also modify because it can decrypt and encrypt to send the traffic to Bob. Okay. So yeah, this is very typical attack on Diffie-Hellman, and of course here you need a kind of authentication. And for authentication, basically, you need what? For authentication, to authenticate that Bob is really Bob.
Yeah, with signature.
You need a signature, digital signature. How to do a digital signature? You need what? How to sign? You need what to sign? Okay, you will have the hash. Okay, but for the hash, you need to do what with that hash? You need, not the private key. You need, if you need to send something to Bob, and you need to make sure that only Bob can receive that, you will sign it with the public key of Bob. So basically here we need public and private key, so asymmetric. Yeah, we need asymmetric. So an asymmetric, it assumes that Alice has the public key of Bob. Okay, this is the assumption. Okay, cannot do anything without having this assumption. But how to distribute these public keys? Okay, so this is the second part of this, or the third part of this lecture, which is public key distribution. How to distribute public key? Because here again we discussed that if Eve can claim to have the key of Bob, or to have the identity of Bob, it will send that message to everybody, claiming I am Bob and this is my public key. Okay, so you can do that if you don't have authentication. So basically here we need a secure way to distribute the public keys. Okay, and this is the public key distribution. People do not need to know a symmetric shared key. Everyone shares a private key and advertises a public key. So you need to know the public keys of all the users. Okay, so for Bob, it needs to distribute its public key. Now, if you are in a small network, okay, and you need to use asymmetric cryptography in limited network, okay, you can have just one trusted center, and everybody has the key of that trusted center, or and it can authenticate. It trusts that trusted center basically. So that trusted center will keep a directory of the public keys of everyone. Okay, whenever someone needs a public key of a certain user, it will just ask that trusted center, give me the public key of X, and it will give. And of course here the communication is encrypted with either the shared key or the secret key between Alice and the trusted center, or the public key of the trusted center. Anyway, this communication is encrypted. Basically, Alice will say, I need the key of Bob, okay, with a timestamp. A timestamp, this is for what? Timestamp here? For freshness. To avoid what? Replay. replay attacks, to avoid storing those packets and replay them some time later. Okay. Then the trusted center will get that public key of Bob. It will send it in clear here with a timestamp. Okay, so this is the public key, and then it will certify that this is really the public key of, or really this is the trusted center. It will sign that timestamp with its own private key, so that Alice can make sure can authenticate that by encrypting it with the public key, decrypting it with the public key of the trusted center. Anyway, this is a simple scenario where you have a trusted center inside the network. Okay. Now, if now if you are in internet, not just one private network. Okay, in internet, how you can get the public key of certain websites which are used by millions of people. Okay. Now the answer here is to use what we call a certification authority. Okay. So certification authority, basically, and we're going to use certificate because here in the previous scenario there was no certificate, just the public key. It is just signed with the trusted center. That's it. Okay. But here we need what we call a certification authority, and we're gonna use certificates that will, which is an evidence that the public key is authentic one, is genuine. Okay. So there will be what we call a CA, certification authority, which is a kind of a trusted entity in the system. It is trusted. Okay. Because again, all the cryptography and this authentication and satisfying these security properties, they assume there is a trusted entity somewhere in the system. Okay. If those trusted entities are not trusted anymore, all the system will collapse. Okay. We need that. You cannot do any secure communication without a trusted center. Okay. Or trusted entity. So in this case, it's called certification authority. So how it works? The Bob, basically, it needs to use asymmetric cryptography. So it needs a private key, or it needs a private key and a public, a pair. Okay. What it does, it will generate those pairs here. Okay, generates the public and private keys. Okay, there are several algorithms to do that, and you can do it even with Java. Okay, generating the pairs. Okay, now you generate the pairs. And then you will keep, of course, the private key local, and you send the public key to the certification authority. Here, you need to trust that certification authority. Now, the certification authority, it will take that public key, and it will record it into the directory of public keys, okay, with the identity of that user, and then it will issue a certificate. It will generate a certificate. We're going to see what is this certificate. And it will basically take care of advertising or distributing that certificate as containing the public key of Bob. So whoever wants to communicate with Bob, he can use that certificate to communicate securely with Bob. And that certificate is signed with the certification authority private key. This is the signature. Yeah. So basically, if you send it to somewhere else, for example, and it needs to make sure that this is really a valid certificate of a valid public key of Bob. Basically, here the certificate, it will contain two things. It will contain the public key of Bob in clear, in plain, okay, and also the signature. So when Bob when Alice receives that certificate and needs to make sure it's the valid certificate, it will do what exactly? It will decrypt or decode the signature. It will get some value. It will compare it with the plain text version of that public key. If they match, it means it's valid. It's a valid one. Okay, because only CA could encrypted with its own private key, and CA is trusted, so it is valuable. Okay.
Now, the Bob's public key will have to change after a while, right?
Yes.
Okay. Now, if someone came and pretended to be Bob and sent the same public key, and he said that I changed my public key to.
No, but here changing the public keys, they should also go through the certification authority.
Yeah, I sent it to the certification authority saying that I'm Bob and this is my new public key. Well, then it will change it or will overwrite the.
But CA needs to have a way to authenticate.
In this case, there is no authentication. With Bob.
There should be like secure connection or secure.
Yeah, here there should be some way of communication between CA and Bob somehow. For example, the first time you set a public key, okay, the first time you send a request to the certification authority, there should be some physical way to authenticate Bob. Then later on, if you need to change the public key, you will need to use the old one. Okay. So the first time there should be some phone communication, some physical way of authentication. And later on, you will use, of course, to renew, for example, password. You need to know the previous one. Okay. So this is our. Yes.
What will happen to all the certificates once the CA private key change?
If the CA private key change, so you need to. There is among the tasks of the certification authority, there is certificate issuing, but also there is certificate revocation. Certificate revocation. So basically, we're going to cover it. It updates the list of certificates. Okay. So, for example, if this month, let's say here the certification authority might have thousands of public keys of users. Okay. So every month you have, for example, 4 or 5 or 10 or 20 certificates are expired. So basically, you need to send a kind of update to everybody. Okay, telling them, okay, this particular list of public keys are not valid anymore, and you need to update them. This is called revocation. Okay, so if, for example, the certification authority of or the public and private keys of the certification authority has changed somehow for some reason, the revocation list will contain all so all of them should be updated.
So
Yes.
how will Alice decrypt the Bob's certification? From where is it? Will you getting the key?
Here, Alice, of course, we just assume that it knows the public key of the certification authority. Everybody knows that. The public key of the certification authority. This will allow it to check if the signature is a valid certification authority signature. Okay? Since if it will use the public key of the certification authority. Okay? So all that it takes is knowing the public key of the certification authority, which is assumed to be known by everybody. Now, what this certificate contains, the most common format for a certificate is the X.509 certificate. So what it contains simply the version, the certificate version number of the X.509, the serial number, the signature algorithm. Here, what kind of algorithm you're going to use? Okay, you're going to sign it with the signature. For example, if you're going to use RSA, for example.
Yes.
Or DS. Asymmetric. Which asymmetric you can talk about? Okay. The issuer name, basically Bob here. Validity period. Okay. From where to where it's valid. The subject name. No, issuer name here, it's the certification authority itself. The subject name is the name of the user, okay, and the public key in clear, okay. And then you have these optional items, and then you have the signature. And the signature, basically, you will sign all this part. All this part, you're gonna sign it using probably the hash. Yeah, you take the hash, okay, of all that value, or all those items, and then you encrypt it with some asymmetric key cryptographic algorithm, and then you have the signature key. So basically, again, the certificate needs to contain two things: some plain text data, which is all this, say the plain text, okay, and the signature part of it, okay. So that to check that all this information is valid, you need to redo the hashing and the signature, or decrypt this to obtain. You need to have the same value. You understand how this is authenticated now?
Actually, yes, but we have we have to decrypt the signature using the public key
Of the certification authority. Yes.
But isn't that obvious that the certification authority advertises also the private key?
It doesn't. How come?
Because
It doesn't.
Because we can compare both. We have the public and they give us a private key.
Yeah, but this is basically what kind of cryptanalysis is this?
We have
One sample.
So basically, you have one plain text data with its corresponding cipher.
But we also have one key.
That's it. So basically, this is.
It's not.
I mean, it's not when it is insecure. When it is insecure, to have several samples of, if you take all the certificates of that certification authority, you will have several samples of plain text, ciphertext, plain text, ciphertext. So you have, let's say, 20 or 30 or 100. Okay. So this is vulnerable when the space of messages is small. If, for example, you know that you need to send, remember the pattern I say. If you know that you need to send a message out of 100 possible messages, okay, then if you have several samples, you can. It's really vulnerable. But here, the space is huge. I mean, even if you have, let's say, 100 certificates, these are 100 samples of plain cipher. Okay, you cannot. Yes. Okay. So this X.509 certificate format. Okay. So among the tasks, we have certificate renewal. Whenever the certificate is expired, okay, you need to renew that. Certificate renewal here. Certificate revocation here. This is not renewal, this is revocation. So basically, in some cases, certificate must be revoked before its expiration. So here, renewal means the certificate is expired, reached its date limit. Okay, you need to renew it, and if everything is fine, it will be renewed automatically. Okay. Revocation at some point, if a user feels that or suspects that its public and private key has been compromised, he will tell the certification authority before the expiration date. Okay, please, this is another or a new one. Please update it. Okay, this is called revocation. Okay, so you will revoke, you will cancel the previous public and private keys. Okay, and you send the new ones. Okay. So certificate revocation, normally it's done at some regular times. Okay, for example, every month or every 2 months. Okay, sometimes some revocation happens in the middle of that period. So in the middle of the month there is a problem. So basically, you have delta revocation. To make revocation more efficient, the delta certificate revocation is a list has been introduced. Basically, if there is something happening in the middle of two cycles, okay, let's say the cycle is every month, and in the middle, let's say after 2 weeks, there is a problem in one certificate. So the certification authority will use this delta revocation list. Okay. So these are the tasks of, and basically all these tasks, okay, of the certification authority and the way to authenticate certificates. This is called public key infrastructure, or PKI. PKI is all that system of sharing on this secure system of distributing public keys and private keys. PKI, very important concept. Okay, so PKI's duty. So here in the PKI's duty, certificate issuance, renewal, and revocation. This is the job of the certification authority. Keys, storage, and update. Of course, the certification authority needs to keep track of all the certificates. Providing services to other protocols like SSL, okay, and providing access control. Here, access control to those public keys. Okay. Now the trust model. Okay. So this is what is happening because we don't really have one single certification authority which maintains all the public keys of every user in the internet. Okay. We have a kind of hierarchy. Okay. So if I don't know, here in the Saudi Arabia, there is for sure one entity that holds the list of, or certification authority to give certificates or to authenticate certificates of local users. Okay, so it's a hierarchy. So basically, users here, this group of users, for example, they will get their certificates authenticated by some regional certification authority, CA1, and that CA1 is certified by the root certification authority. So it's a kind of hierarchy. Okay. Now, suppose here that user 2, for example, wants to send something securely to user 7. So user 7 receives some request with the certificate of user 2. And user 7 needs to check that the public key received from user 2 is valid. So basically, user 7, it will receive what? It will receive exactly, of course, before starting the communication, it will receive the certificate. It needs to know the public key of user 2. So user 2, basically, it will do the following. It will send two things. Okay, two things. User 2, let's say public key. Okay, user 2 public key, and basically also CA1 user 2 public key, and by CA1 user 2 public key it means the certificate of the public key of user 2 issued by CA1.
Yeah.
Okay. Then it will not only send that, it will send all the certification chain. Basically, here it's not enough. CA1 might be not known by user 7. It is not known here. Okay. So here, user 7 let's assume it has just the public key of CA, the root, just that. Okay. It doesn't have the certificate of CA1. So if you send it, if it receives like some value certified by CA1, it will say who is CA1. Okay. So again, user 2 will send also CA and CA1, basically the certificate of the public key of CA1, certified by the root certification authority. Okay. So basically, it's a chain. This is just 2 levels, but if you need to send your public key to someone else, okay, and you need that other party to be able to validate that public key, you need to send the chain up to the root, okay, so that the destination can be able to check. Okay. Now here, user 7, it does what? Here, user 7, again, we assume that it knows the public key of certification authority. It will check, okay, I received this public key, it is certified by CA1, I don't know CA1, but the user 2 also sent me the certification or the certificate of CA1 by CA. So it will, and of course here it will have the CA1 public key, right? This one, CA1 public key. So it will do what? It will take that CA1 public key and basically to validate that this is the public key of CA1, it will decrypt this with the private key of CA, right? it needs to check that this is really the public key of CA1, right? So what it needs to do? Now, user 7 received this.
Yes.
It needs to check this is valid, this is a authentic public key of CA1. What it needs to do?
Decrypts it with the public key of CA1.
Yeah, it will decrypt because this is, when we say this, it is signed by the private key of CA.
Correct.
So basically, it needs to decrypt this, all this, with the public key of CA. It must obtain what exactly? It must obtain this. So it will just check. So once it finds that, it's sure that this is the public key of CA1. Okay. Then it will use that public key of CA1 to decrypt this. Right? It will decrypt this. It needs to obtain what if it decrypts this?
Public key of
Public key of user 2. It will check it with the one sent by user 2 and to make sure this is the valid one. So basically, it followed the chain up to some common trusted entity, which is CA here, and it validated that. Okay.
But we don't decrypt, we encrypt with the public key, right?
Yeah. We encrypt, but we call it decrypt because it's already encrypted with the private key. So when you encrypt with the public key, you're basically decrypting. Okay. So this is the example I just explained. Now it's explained here. Okay. Yeah. Now, if you need to know, if you want to see the list of certificates that you have, because you are using certificates all the time. If you need to use the software tool which uses extensively certificates is what?
Browser.
The browser, the web browser. So if you open the web browser, you're going to see a list of certificates. Okay. So this is an example with Firefox.
How much is the maximum
Number. I don't think there is a maximum. Depends on the memory you have. But, okay. So here, if you go to options, then
security.
I think advanced, and then certificates, right? And view certificates, okay? And you have all the certificates.
Oh,
Yes, so it's a long list of all certificates. Now, use it. There are certificates already stored that comes with Firefox, okay? You don't need to get them, they are there installed with Firefox, okay? So if you open any one, let's say, I don't know, this one, for example, view. So you see here, fingerprint, SHA-256 fingerprint, SHA-1 fingerprint begins September 30, see how much period of validity?
34 years.
30? 34 years, you know, 34 years. So it's quite secure, basically. Okay. Issued by Chambers of Commerce root, organization AC Camera Film. This is the I think the certification authority. Okay. Anyway, so you have full list of all the certificates. See here, certificate field, version 3, serial number, certificate signature identity, public key, subject key, RSA encryption here, subject, certificate signature algorithm, SHA-1 with RSA encryption. You see? Okay. So yeah. Now, suppose you have a website, you set up a web application, you put it online, and you need to have, let's say, online payment, or you need to authenticate users. Okay. So basically, if you need to use HTTPS secure protocol, you need what? You need a certificate. So how to get the certificate? So we know the process. We know it now. Basically, you can use any algorithm to generate the public and private keys, and then the important step is to get it certified. So you need to contact some certification authority, and it needs to send you some certificate. So, of course, certification authority will do it for you, but you need to pay. Okay, so you need to pay. So I went online. I wanted to check some examples.
So I went to one known certification authority called VeriSign. You know VeriSign? Huh?
Yes.
So yeah, VeriSign has been owned by Symantec, by the way. So this is the example of SSL certificates used with SSL, with HTTPS basically, and to have secure secure feature in your website. Okay. So these are examples of the different variant. Okay. So basically, what you have here: secure site with EV, secure site Pro with EV, secure site, secure site. So this cheapest one is $400 a year. Okay, for the certificate, and you have a couple of options like renew, like price 1 year. So for example, if you need that green address bar that appears whenever you go to secure website, you need to have pay at least $1,000. Okay, yeah, per year.
Like this one.
Yeah, like this one.
So
Yes.
this one is
Yeah, because these details will provide assurance to whoever. Yeah, and it's all about that. If you need to pay, I don't know, if you want to, there is a new website, and you need, it asks you for your credit card, okay? So me, for example, I will make very sure that this is a trusted website. So if I have that, I'm quite a little bit assured, okay?
the warranty.
Warranty, yeah, it has warranties, how much? $1 million, huh?
Yeah.
$1 million, yeah, $1 million. So assurance if it gets broken. Yeah. So there is one feature, this ECC, strongest security. ECC, strongest security, basically is for these two options. And ECC, basically, this is another asymmetric key cryptography, more secure than RSA. It's called elliptic curve. Elliptic curve cryptography. I think in 454 course you didn't cover that. So it is more secure. Basically, the key will be shorter. The key will be shorter, and it will be much secure. For example, here it says. If you go here. Yes. See what it says here. ECC elliptic curve cryptography with semantic ECC provides strong security and high performance also. Okay. With a shorter key size when compared to the current dominant encryption method. For example, an ECC certificate with 256-bit key is stronger than the RSA certificate with the 2048-bit key. Okay. So it's additional security. And from the price, you see it's really a secure option. Now, another question. Does the certification authority keeps your private key? It depends on with which certification authority you are dealing. Because you can ask the certification authority to generate both the private and public key. This has the advantage that everything it can be decrypted by the certification authority, basically. The advantage of doing that, okay, the advantage of doing that is that you have a backup version of your private key. Because if you lost your private key, if you lose your private key, which is stored somewhere locally, somehow, basically you will not be able to decrypt old messages, right? You can renew it, or even renewing it, it's a problem. Okay, renewing that certificate is a problem. Yeah. So it's a backup version. So if you want to really trust the certification authority, you can ask it to generate both the private and public key and keep the copy of the private key. Okay. Yeah. So that's it for PKI. So next time we're gonna see how we can use all those algorithms. We saw several of them. We start to use some of them here. Basically, digital signature, asymmetric key cryptography, etc. Next time we're gonna see how all this can be used in SSL, which is the main protocol for secure communication. Yeah. So questions? Clear? Okay. So let's stop here.